Okay, now I'd like to do from still page, I guess now it's page 258, 259. I'd like to do C1 first. So they give us a diagram for our interpretation now. And, they're giving us numbers for these things. I'm a little uncomfortable using numbers because I thought they told us earlier that names are, uh, lowercase letters, but it's okay. We'll use numbers. It's fine. And let's look at this diagram before we do anything. So here's 1, and it's self, arrowed. Then here's 2, and then here's going down to 5, and it's self-pointing. We have an arrow from 1 to 5. We have an arrow between 1 and 4. And we have an arrow from 1 to 3. So this is encoding, a relation, essentially. They're calling it R in this case. So what they're saying here, what this is telling us, this means, if you go back through the lecture or read the book, an arrow from one place to another is it's saying that R12 is true, okay? And I'm not going to write true every time, but anything that starts somewhere and ends somewhere, you write it in order of start point, end point, and then you get that relation. So if I have an arrow from 1 to 3. I have an arrow from 1 to 4. I have an arrow from 1 to 5. And that's all of them that start with 1. There's 1, 2, 3, 4, 5 of them. But then I also have an arrow, so that takes care of, let me mark them so I don't forget one. Done that one, that one, that one, that one, that one. Let's do this other one from 4 as well. So there's an arrow going from 4 to 1. So that's done. And then there's also an arrow from 2 to 5. So they're saying all these are true. And that's just a way to, define this predicate, this two-place predicate. Okay, it's a convenient way to do it. And it's kind of neat that you can use a graph. It's called a graph in discrete math. It's called a graph. There's a whole graph theory out there that you can do a lot with. A lot of combinatorics and computer sciencey kind of stuff is done in graph theory. There's a lot of applications of computability and complexity theory in graph theory and so on. But I want to look at C1. C1 is the question. There exists, is this true or false? Is this sentence true or false? There exists X, RXX. Well, that's just the question. Is there something in my list of relations, or in other words, in my picture, these are the same thing, they're encoding the same information. Is there something that is in the same position twice? Oh, I forgot one, didn't I? R55. And in fact, there are two, right? There's this loop here and this loop here. So this is true. And that's because you could let X be 5. All right? And if you did that, then that would work. Okay? I kind of want to write equals there really bad, but I'm going to not do it. Okay. Let's look at C5. C5 is for all X, for all Y, for all Z. And then it says RXY and RYX implies RXZ. Let's see, did I do the parentheses right? These match, yes. Now, you may recognize this statement as something, right? Maybe you're already thinking about it. Well, okay, actually it's not. It almost looks like the transitive property, but it's not. Okay, transitive property would require like xy, yz gives you xz, but this thing screws that up. in C5. So, oh no, I just miscopied it. My apologies. So it's RXY, RYZ. There's a Z here, not an X. Implies RXXZ. So this is really a transitive property, okay? Now, some interpretations will obey a transitive property. Other interpretations will not. So the question is this a transitive relation? That's the question we're asking here. So how will we answer it? Well, it's kind of intensive, computationally intensive. I have to check, whether this implication holds. Now, it's more likely that it's not true, right? Because, there's a lot of missing gaps between these things. So maybe we should look for a counterexample, okay? So if we found an X, a Y, and a Z, such that this implication was false, again, I don't know if that's the answer or not, I'm just thinking through it here, then we would fail to have it holding for all X, Y, and Z. The only way to know it does hold for all X, Y, and Z is to check everything. So my guess is probably this is going to be false. So maybe let's just think about some examples. So, maybe if I let X, Y, and Z all be the same thing, right? So if X were 1, Y were 1, Z were 1. Now I'm allowed to do that because the for alls, they can pick anything in the domain. My domain here are these numbers, 1, 2, 3, 4, 5. That's my domain. Now technically I should be giving these things letters for names, but I'm just going to stick with the symbolic numbers here because it's easier. And I'm not going to fault you if you're not super careful about that. I could call 1 O and 2, I couldn't call it T, it's too large, right? Because that'd be a variable. It gets messy, and who cares? Let's just use the symbols. If I let this happen, then this thing would become R11 and R11 implies, and these are in parentheses, implies R11. Well, that's true and true implies true. That's true. That's working. So this thing is not a counterexample to this thing being true. So we need to pick other numbers maybe. So maybe I pick... Now 1's going everywhere, right? So, if 1 is the first thing, then no matter what the second thing is, it's going to be true. So maybe I don't want X or Y to be 1. Maybe I want maybe 2 to be one of them. Maybe I take X to be 2. Let's take Y. We could let Y be 1, right? And we could let Z be 5, for example. I just kind of picked those out at random. But if I did this, so that gets rid of these quantifiers, and I'm left with R2, 1 and R1, 5 implies R2, 5. Now, let's make sense of this. R2, 1 is false, right? So that is a false. There is no arrow from 2 to 1. R1, 5 is true. And R2, 5 is true. So what is this? This is false implies true. But false implies true is always true. So again, it was true. So it seems like what we want to kind of make a counterexample happen is we want to make sure that both of these ones are true, but we want this one to be false. If we can do that, then we got it. Okay? So let's see. So we clearly can't, so if X were 1, then this thing is true, and that defeats the purpose. So we need maybe let's try I'll decide what x is in a moment. No, let's see, I want the left side to be true and the right side to be false. So maybe if x were 2, I could pick z to be 4. That's going to make sure that rxz is false. Now I just need to make sure that the y I pick starting at x is 2, so y has to be something that 2 maps to, so y has to be 5 in order to make this one true. And is it true that y goes to z, 5 goes to 4? It's not. So this one would be true and false implies true. Again, that's false implies true, and that's true. It might be that it is transitive. I wanted to avoid having to check that all the time. But I guess we need to go down that path. So what I'm going to do is replace some of this paper with new paper, and we'll just kind of systematically try to check it. If we keep in mind that if the left-hand side of the implication is false, then the entire implication is true, that'll help us, okay? That'll help us. So maybe it's true. Maybe true, okay? Let's see. Maybe I'll put that right there. Maybe it's true. So how will we check that? So first off, if x, so we have a domain here of 5 numbers, and x, y, and z could be any of these. Okay, so the first thing to realize is if x and y were both 1, then it's true. Okay, no question about it. Why? Because that would make this one true, because 1 maps everywhere, and that would make this one true because 1 maps everywhere, and that would make this one true because 1 maps everywhere. So for all z, that's done. Okay? But what if x was 1 and y was 2? Well, x is 1 is basically always true in this relation, so that's no problem. But if y is 2, then the only thing that could make this true, this forces. In order to make the and here true, so this is going to be okay, but in order to make this and a true thing, it has to be the thing that 2 maps to, that points to. So we're forced to take z equal 5, okay? Otherwise it's false, okay? And false, okay, if it's false, then we're done, because of, like this example, okay? So, we're still seeking a counterexample, but we're kind of going at it systematically at this point. Now, in this case, x equal 1, y equal 2, z equal 5, did we do that one already? No. So if x equal 1, y equal 2, and z equal 5, you would have r1, 2, and r2, 5 implies r1, 5. And that's true and true implies true, because 1 maps to 2, 2 maps to 5, and 1 maps to 5. So it's some kind of triangle going on there. So maybe that's a key. Maybe if we try to make a triangle, maybe 1, 3, and 4 are a way around it. Let's see. If we, I'm convinced it's not true. If I set x to 1, no, I don't want x to be 1 because of the right side. So if I set x equal to 4 and y equal to 1 and z equal to, let's see, maybe 3. What do I get there? I'll get R 4, 1 and R 1, 3 implies RXZ, R4, 3. Now, R4, 1 is true. 4 has an arrow beginning at 4, ending at 1, so that's a true. R1, 3, there's an arrow starting at 1, ending at 3, that's a true. Aha! Implies R4, 3. So 4, 3 would require an arrow from 4 to 3. There is no such arrow, that's a false. So this is a true implies false, and that's a false. So what do we conclude? After a lot of searching, and we had to look at many cases to get to this point. I wanted to avoid showing every possible case, because how many cases would that be? That would be 5 times 5 times 5, 125 cases to go through. Didn't seem feasible. Okay, so we lucked out. This is false. So this implies that the statement, I should say the sentence, is false in this interpretation. Now, if I had a different interpretation, a different picture, where everything was connected to each other, for example, then of course this is true. But there are some weakenings of that as well. The question of how many interpretations, make this statement true, that's an interesting question. And it's a question of, how many transitive relations on 5 objects are there? Okay, there are ways to, those are interesting questions from, say, a certain perspective. Okay, there are people that make careers out of questions like this of, well, okay, how many transitive symmetric relations are there? How many transitive symmetric reflexive relations are there? There's all kinds of interesting questions, and once you get so many elements, it starts becoming computationally, difficult to compute them, to find them, to count them. So there's a lot of interesting combinatorial mathematics involved, even in the simple question of transitivity, let alone adding more and more properties to these things. So that's C5. Let's go ahead and also look at C10. Now that you're starting to see the flavor of this stuff, it's kind of interesting, because we're now getting into the case where we're seeing things that we recognize from mathematics. I mean, the transitive property, if A is less than B and B is less than C, then A is less than C. You've seen that before. You've used it. Okay, we're just calling less than R instead of less than. Let's look at C10. Now again, we have this same interpretation: 1 mapping to itself, to 2, to 3, to 4, to 5. 2, they put 5 down here, and 2 maps to 5. We have 1 and 4 kind of, symmetric, and 1's mapping to 3. So C10 is the sentence: there exists X such that for all Y, RYX if and only if X equal Y. RYX if and only if X equal Y. Okay, so how do we interpret this? Now, equality, again, is all about objects in the domain. Okay, so X equals Y means we're talking about the same name is given to the same a different name is given to the same object. So what's saying is there is one thing in this picture with the property that no matter what other thing you pick, the only time you have a line from Y to X is when X is Y itself. Now that's a strange kind of thing, but if you think about it, it's all about self loops essentially, because if R goes from Y to X, then that means that okay, X equals Y. Now, is this true or not? So 5 and 1 seem like pretty good candidates to play with here. So let's just work out sort of what this sentence means in some cases again, and see what we kind of come up with. Until we play with this, we can say it, but understanding what it's saying is a whole different matter. So let's say I let x be 1. Okay? If x is 1, then I have 5 options. Okay? I can have y equal to 1, 2, 3, 4, or 5. Okay? So, in these options, what happens? Well, if y were 1, if y were 1, this becomes the statement R 1, 1, if and only if 1 equals 1. And I'm just going to write these down, and then we'll analyze them, okay? Then it would say, if y were 2 and x were 1, if y were 2, then it would say R2, 1, if and only if 1 equal 2. And then this would say R3, 1, if and only if 1 equal 3. And R4, 1, if and only if 1 equal 4. And R5, 1, if and only if 1 equal 5. Now, we only get a problem if one of these, so there's a problem if one of these ends up false. The problem would only exist on the for all part of this this sentence, because it might not be that x is the one that exists, right? So we would have to check the same thing. If one of these ends up false, then we move on to x equal 2, and then we do the same thing. If one of these is false there, then we move on to x equal 3, and so on. So let's check the truth of these things. I'll use red for this. So R1, 1, well, that's true, right? That's true. And 1 equal 1 is true. This if and only if is a true. R2, 1, is there an arrow from 2 to 1? Well, that's false. Is 1 equal to 2? No, that's false. But if and only if just checks if they're the same, right? So that's also true. Looking pretty good. R3, 1, there is no arrow from 3 to 1. So that's false. But this is also false. So false and false is a match. So it's a true. R4, 1, well, that's actually a true, right? Because there is an arrow starting at 4 and ending at 1. So that's a true. We have an if and only if and 1 equal 4, that's a false. Uh-oh. We end up with a problem, right? We end up with a false. So what's that mean? That means that the for all part of this, it's not true. There is x equal 1 is not an x with the property that all this holds. So we're looking at this part of it here. Okay. So if this is my x, then we're asking the question, for all y, ry1, if and only if 1 equal y. And that's false. That's not true anymore, right? I shouldn't say anymore. It's just not true, because this 4 is a counterexample. So now we can't just stop, okay? Because if we had a for all out here, okay, then that would be enough to sort of finish it. But this just says there exists. It's just saying, well, there's one of these elements that if I do all this stuff, then it works. But we just ruled out 1 being that element. We did not yet rule out 2, for example, of being that element. Now, if you think about this sentence, you can easily rule out 2, 3, and 4. Why? Let's look. If x were 2, and I let y equal 2, then what I need to be checking is, if x and y were both 2, R2, 2, if and only if 2 equal 2. Well, excuse me, 2 equal 2 is a true, but 2 does not self-loop. That's a false. And right there is a false. Now, you get the same kind of argument if x were 3 and y were 3. and if x were 4 and y were 4. These all will sort of work the same because none of them have self loops. So the only other option we have here is to consider 5, x to be 5. And I don't know what's going to happen because I didn't do this in advance. But we want to look at now the sentence, for all y are y5 if and only if 1 equals, if 5 equals y. Now, if you think about it, it's saying something maps to 5 only if it's 5 itself. I don't think that's going to be true. So we look at our options. Y equals, if y was 1, then this sentence becomes R15 if and only if 5 equals 1. Well, 5 equals 1 is certainly false. And R15, well, there is an arrow from 1 to 5. That's a true. So already out the bat, we're getting a false. So what's this mean? We've ruled out 1, we've ruled out 2, 3, and 4, and those were all sort of the same. And then we ruled out 5. That's everything in the domain. So what's this mean? There is no such x. So the sentence is false. Now, there might be a way to, upgrade this to make it true. For example, if we got rid of this line here from 1 to 5, then this one would be true because there would now be no longer a line from 1 to 5. And I think all of the others would be true in that case because if y were 2, 3, or 4, then this side would be false, but 5 doesn't map anywhere other than to itself, and so those would all be, the if and only if would end up being true. And then if y were 5, you would have a true if and only if true, and that would be true. So if you got rid of this line, you would end up with something for which that statement holds. There would be such an x that the only thing that maps to x is itself, essentially, is what it's saying. But we don't in this particular interpretation. So again, deciding the interpretation you're using is a big part of mathematics, but we're at this level of investigating given interpretations. Mathematicians go further and pick interpretations to do certain things, and we will later as well.